one independent variable. For example, example 1 and example 2 you can consider, whereas partial differential equation involves more than one independent variable, as you can see in example 3, Laplace equation. Again, ordinary differential equation can be classified into two parts, linear and non-linear. Linear, when we say, it is differential equation of first degree, and non-linear when we are saying it is more than 1 degree, or you can say that is unknown function multiplication with its derivative or with itself is there. Now solving linear ordinary differential equation is quite simple, whereas for non-linear differential equation solving is a bit difficult, but there are different other methods of solving non-linear equation also, like numerical method is there. We will be talking about solving ordinary differential equation, as I said in the earlier. Since most of the physical problems, especially in engineering, are of the form of second order linear ordinary differential equation, like mechanical problem or electric circuit and all. So I will be talking about second order linear differential equation. Again, method of solving this is very easy, and we can extend this second order equation to higher orders also by the same method. So using this method, we will understand how to solve it. Say some equation of the form ax d2y by dx square bx dy by dx plus cxy equal to dx, where ax, bx, cx, dx are either constant or continuous in the interval I. If dx is 0, we call the function to be homogeneous. That is, all the terms are of same degree. Whereas if dx is non-zero, we call the differential equation to be non-homogeneous. For example, example 4 is non-homogeneous, whereas example 5 is homogeneous, because RHS is 0, you can just see. We can convert our first we'll talk about homogeneous differential equation only, linear homogeneous differential equation. We can convert into standard form this. We have to take care that this ax is non-zero, because if ax becomes 0, then this is not of second order equation. So since ax is non-zero, we can divide the whole equation by ax and write it in this form, where px is nothing but bx divided by ax, and qx is nothing but cx divided by ax. This is the standard form of writing the equation. And if we want to find the solution of the differential equation, that means we need a function of x such that when we simplify or we take second derivative, first derivative and all, and substitute in the equation, we get RHS equal to 0. So we need a function fx which satisfies this one. Say, and the simple one, as you know, we can say is e to the power mx. But before that, we have two fundamental results which is important for writing the solution of the second order equation. Second order equation, okay, tell me how many solutions we should have in second order equation? Can anyone tell me? If I am having nth order linear ordinary differential equation, then in that case we will have n number of linearly independent solution, we say. Since we are talking about second order equation, we will have two solution, and the two fundamental results says that, first one says that if y1 and y2 is two solution of this second order equation, then its linear combination will also be the solution of the equation, which we call it as superposition principle. Say suppose y1x and y2x is the solution of the equation, then this implies that ax, let me write in short, that is y1 double dash plus bx y1 dash plus cx y is equal to 0, being y1 solution. Similarly, I can write now we have to prove that this yx is solution of the equation. Then let us substitute this value in our differential equation. We will have ax that is differentiating y once, differentiating y again, you will get something of this form. Now taking C1 common, you will have equation of the form ax y1 double dash plus bx y1 dash similarly C2 also you will get something. Now we already know that this, because y1 is solution of the differential equation, this is 0. Again, this will be also something of this form only. So we see that if y1 and y2 are solution, then its linear combination is also solution of the equation. And this, from this, it establishes the following, that is, if y1 and y2 are solution, then their sum is also solution by taking c1, c2 equal to 1. Again, k y1 will also be solution by considering c1 equal to k. Even y equal to 0, or you can say yx equal to 0 is also solution. We call it as trivial solution by considering c1 and c2 as 0 from the same theorem. Again, the second fundamental result says that these two solutions, whatever we are talking about, should be linearly independent also. The reason is, since it is second order equation, in my general solution, I should have two arbitrary constant. Say suppose y1 and y2 are not linearly independent, then my solution I am writing in this form, fine, c1 y1x plus c2 y2x. But since y1 and y2 are linearly dependent, I can represent y2 as some combination of y1 or some function. So let me write c1 y1x plus some value, say c3 y1x, which is nothing but I am getting only one arbitrary constant. Therefore, for general solution to exist, we should have two arbitrary constant, and for two arbitrary constant, our solution should be linearly independent. Dependent solution is there, fine, but two linearly independent is must for second order. Similarly, for third order we are talking about, then we will have three linearly independent solution, and we have this theorem. We can prove this theorem for the same. Now we will focus on first solving homogeneous differential equation with constant coefficient. That means our coefficient of second derivative, first derivative, and y are constant in place of function of x, you can say. Then, as I said, for finding the solution, we can consider a simple function, say y equal to mx. Say if I am assuming that y equal to mx is solution of the equation, that means it should satisfy the equation. So y dash, let me take y equal to the power mx. Similarly, y double dash, if I consider, it is m square e to the power mx. I know most of you already know all these things, because yesterday only I was hearing auxiliary equations so many times. So, but still let us revise it. So when I substitute this value in my equation, I will be getting a m square e to the power mx plus bm e to the power mx plus c e to the power mx, and this equal to 0. If I take e to the power mx common, I will get am square plus bm plus c equal to 0. Now we know that e to the power mx will never be 0. This implies that we should have am square plus bm plus c should be equal to 0. This is algebraic equation, and we call this equation to be auxiliary equation. And since it is quadratic in m, we can find the solution of this one as m equal to minus quadratic solution method b square minus 4ac divided by 2a, and depending on the discriminant value b square minus 4ac, we will have two solutions of different form. Say first one, suppose b square, that is case 1, you can say, suppose b square minus 4ac is greater than 0. Then I will have solution as m1 equal to minus b plus b square minus 4ac by 2a, m2 equal to minus b minus b square minus 4ac by 2a. And as you can just see, both the solutions are real and unequal. That means we assumed, we started with that let y equal to e to the power mx is the solution. So this indicates that e to the power m1x and e to the power m2x are two solutions of the equation, differential equation. And since these two are solution, or you can say y1 and y2, that means its linear combination is also the solution of the equation. So in this case, we will have y equal to this value. You can say if b square minus 4ac is greater than 0, we will have solution as y equal to c1 e to the power m1x plus c2 e to the power m2x, where m1 and m2 value just now I have written. And this establishes this theorem, that is, if m1 and m2 are two real and unequal roots of the auxiliary equations, then c1 e to the power m1x, c2 e to the power m2x is the general solution to this differential equation. For example, if you are asked to solve this equation, we can directly write auxiliary equation as m square plus 5m plus 6 equal to 0, which gives me m plus 2 into m plus 3 equal to 0, or you can say m is equal to minus 2 minus 3, two real and unequal roots. So my general solution of this equation will be c1 e to the power minus 2x plus c2 e to the power minus 3x. Again, depending on the discriminant b square minus 4ac, say suppose it is 0. B square minus 4ac is 0 means my right side part, that is minus b plus minus b square minus 4ac divided by 2a was my m value. This part is 0. That means I will have m equal to minus b by 2a, or you can say m1 and m2 equal to minus b by 2a. And now you can just see, if I consider solution as y1 equal to e to the power m1x, y2 equal to e to the power m2x, then they are not linearly independent. Sorry, not m2, it will be. Then you can see yourself that they are dependent, but I need linearly independent solution. In that case, we multiply first solution, we will take y1, and for the second solution, we multiply this by simple function or simple polynomial, say x. Then in that case, y2 will be equal to x e to the power m1x. This is possible. The reason is, say suppose my equation was a y double dash plus b y dash plus cy equal to 0, and I am given that y equal to e to the power mx is the solution. If I want to prove that x to the power m1x is also solution, let me substitute this value and its derivative in this equation and check it. First derivative, y is equal to this we are saying. So y dash is equal to e to the power m1x plus m1x e to the power m1x. Similarly, y double dash, if I am finding out, it will be m1 e to the power m1x plus m1 e to the power m1x plus m1 square x e to the power m1x. Substituting these values in this equation, let us see what we are getting. A, then second derivative is twice of m1 e to the power m1x plus m1 square x e to the power m1x plus b e to the power m1x plus m1x e to the power m1x plus c x e to the power m1x. Further simplify this one, you will get, if you further simplify this one, you will find, just tell me what we will be getting in this case. So if I take x part common, I will be getting a m1 square x e to the power mx. I am taking common, x e to the power m1x common. Then this term plus b m1 plus c, this term. Again, now let me talk about the second term, that is e to the power m1x, then a 2m1 plus b equal to 0. And you know that because e to the power m1x is the solution, so auxiliary equation gives me a m1 square b m1 plus c equal to 0. So this part is 0. Again, we have seen that m1 is equal to minus b by 2a, or if you simplify this, you will get 2a m1 plus b is equal to 0. That means the second part is 0. So whole equation is 0. So that because of this reason, we can consider the second solution to be x e to the power m1x. Similarly, if suppose I am having third order equation and all m1, m2 and m3 are equal, then in that case I will consider the solution to be e to the power m1x as first, second one as e to the power m1x, third one as x square e to the power m1x. And this, from this we have the theorem, that is, if m is a repeated real root in the auxiliary equation, then our solution will be of this form, because one of them is e to the power mx, the second one will be x e to the power mx. For example, if I am talking about this equation, its auxiliary equation is nothing but m square plus 6m plus 9 equal to 0, or you can say m plus 3 square equal to 0, or m equal to minus 3 minus 3. Therefore, I can write y equal to c1 plus c2x e to the power minus 3x. Now this was the case when my b square minus 4ac was 0. Suppose b square minus 4ac is less than 0, or you can say my m is then a solution for this one will be, I can just take minus sign, or if this value is negative, I'll make it positive by multiplying by minus 1 and taking it out. So we will have our solution to be something, or you can say we have solution of the form alpha plus minus I beta, or imaginary solution where alpha is equal to minus b by 2a, beta is equal to root b square minus 4ac by 2a. And for writing the solution of this one, we can say C1, that is, you can say y1 is equal to e to the power alpha plus I beta, y2 is equal to e to the power alpha minus I beta multiplied by x. The general solution will be y equal to C1 e to the power alpha plus I beta x plus C2 e to the power alpha minus I beta x. This we can further simplify and write it in the form of e to the power alpha x a cos beta x plus b sin beta x. That is, if you cos and sine form, simplify that, we will have the solution for that one. And this, from this we have this theorem. For example, if I'm having this one, the auxiliary equation for this one is equal to m square plus 4m plus 9 equal to 0, where m is equal to minus 4 plus minus 16 minus 36 divided by 2, or minus 4 plus minus 2 root 5 by 2, or you can say minus 2 plus minus root 5. So alpha and beta we are having, alpha is minus 2, beta is root 5. My general solution, I can write it as e to the power minus 2x bracket c1 or a, whatever you want to write, cos root 5x plus c2 sine root 5x. So depending on b square minus 4ac, there are three method or three different forms of the solution of homogeneous linear ordinary differential equation. Once we have the solution of homogeneous ordinary differential equation, we call this solution to be complementary function also, or you can say general solution for homogeneous equation. Now this general solution, if you want to find the particular solution for this, then since you are having two arbitrary constant, we should have two conditions. Both this is possible by specifying the solution at some particular point, solution and its derivative at single point, you can say some point x naught. We are saying y x naught equal to some value y naught, y dash x naught to the value y1. This condition we call it as initial condition, and this type of problem we call it as initial value problem. And based on this we have theorem, that is, if ax, bx, cx and dx are continuous through an open interval I, then there exists a unique solution yx satisfying this equation, and the condition is this one, that is, condition is on single point. For example, if you are having this value, this we have already solved it. Solution of this one is, what was the solution of this? Okay, let me write it only. Auxiliary equation was 6m plus 9 equal to 0, or you can say m plus 3 the whole square equal to 0, m equal to minus 3. So y was equal to c1 plus c2x e to the power minus 3x. Now substituting x as 0, you will get 1 equal to c1. Then differentiate this equation and substitute the value of y dash, you will get the value of c2 also. After substituting both the solution in this equation, we will get the particular solution. This was the case when we are specifying the values of y and its derivative at single point. But we can also specify the values of y at more than one point. Say here, because it is second order, I need two conditions. So at 2 points I have considered. This type of problem we call it as boundary value problems, and the condition we call it as boundary conditions. In this case, it's not necessary that our solution will be unique. For this particular example, it is unique solution. The process of finding is same. You find the solution of this one. This is nothing but m square plus 9 equal to 0, or m equal to plus minus 3i. My general solution will be y equal to c1 cos 3x plus c2 sin 3x. Find y0, find y dash 0, sorry, find y0 and differentiate y and find pi by 12. Two condition, two unknown, you will get the values of y1 and y2, and you will get the particular solution of the differential equations. Now let us, this was the previous part when our RHS value is 0 or homogeneous equation. Now let us talk about the case in which our RHS is non-zero. It is any function of x or constant. For simplicity, first I am considering the case in which a, b and c are constants in the open interval I. Then as you know that if my differential equation is this one, then my solution is c1 y1x plus c2y, because I will get two linearly independent solution. I can write it as linear combination of y1 and y2. Let me denote it by yc, that is complementary function we also call it. And suppose yp is the solution of the equation 1, or you can say when we substitute yp in this equation, it satisfies. And then in that case, we say that the general solution of the equation is, equation 1 is, because this is a particular value you will be getting from here, it will be yc plus yp, because yc will take care of the arbitrary constants. We can prove it also. Substitute this yc plus yp value in the equation 1. I have substituted it. Simplify, you will get RHS. Or other way also, we can say that yc is general solution of the homogeneous equation. That is when RHS is 0. And from this we have a theorem 7, and this is quite important because we use this for solving the nonlinear equations. The general solution y equal to yx to the non-homogeneous differential equation has the form y equal to yc plus yp, where the complementary solution yc is the general solution to the associated homogeneous equation, and yp is the particular solution to the non-homogeneous equation. Now, for finding this yp particular solution, there are different methods given. We will be talking about variation of parameter method. We can variation of parameter method is quite powerful method, because in this case there is no special case for dx, that is my RHS value can be any function of x. There is no restriction on this, and our ax, bx, cx may be constant, or it can be continuous function of x also. The only thing that is important for us in this case is that we should have two linearly independent arbitrary constant if our equation is of second order. If it is of third order, then we should have three linearly independent solution. Or you can say otherwise, that we should have complementary function. If we have the complementary function, then we can solve the equation. So say suppose I am already having two linearly independent solution y1x and y2x. Then we know that c1 y1x, c2 y2x is also the solution of the differential equation. Okay. Now for finding yp, or you can say for finding the general solution yx, we assume that c1 and c2 are not constant, but they are function of x. Or you can say c1 and c2 are variables, which we write it as v1x and v2x. So we assume that our solution is yx equal to v1x y1 plus v2x y2, where at this stage in the starting we don't know the value of v1 and v2. since I have to find two values, that means I need two conditions. One condition I can get it by finding y dash, y double dash and substituting in the equation 1. Second condition is up to us, depending on what values we are getting. We can assume the second condition. So once we have two conditions, we can get the values of v1 and v2. And once we have both the values, we can substitute in our yx, and that is our solution. So yx is given like this. Let me, for simplicity, let me write y equal to v1 y1 plus v2 y2, because it will be easier for me to write. Then y dash is equal to v1 y1 dash plus v2 y2 dash plus v1 dash y1 plus v2 dash y2. Now, since I need two conditions, what I will do is, one condition I will take that this derivative of v part to be 0. So one equation now I am having is v1 dash y1 plus v2 dash y2 equal to 0. So I have one condition. Now my y dash changes to, because this I have already considered to be or assumed to be 0. So it will be v1 y1 dash plus v2 y2 dash. Again differentiate y dash, you will get y double dash equal to v1 y1 double dash plus v2 y2 double dash plus v1 dash y1 dash plus v2 dash y2 dash. Now we will substitute this y dash and y double dash in our original equation and simplify it. We will get one equation we are already having for condition, for we're getting v1 value. So when you will simplify, my equation was ax y double dash plus bx y dash plus cx y equal to dx. So ax y double dash is v1 y1 double dash plus v2 y2 double dash plus v1 dash y1 dash plus v2 dash y2 dash plus bx is v1 y1 dash plus v2 y2 dash plus cx is v1 y1 plus v2 y2 equal to dx. Let us simplify this. Yes, what we will get if we simplify this, y1 double dash and y2 double dash part, let me take at one side, or you can say v1 dash and v2 dash part, let me take at one point, and let us see what we are getting. Simplify this one and tell me what you will be getting. Take care that since y1 and y2 are solution of this equation, that means ax y1 double dash plus bx y1 dash plus cx y1 is equal to 0, because y1 is solution of equation this equal to 0. So this is 0. Similarly for y2 also. So let me write for that form only. Let me take v1 common. So v1, if I am taking common, I will get ax y1 double dash. This similarly bx y1 dash plus cx y1. Similarly, take v2 common. You will have ax y2 double dash plus bx y2 dash plus cx y2 plus, now I am left with these two terms, that is v1 dash y1 dash plus v2 dash y2 dash, and this equal to dx. Since this is 0, this is 0, I have equation v1 dash y1 dash plus v2 dash y2 dash equal to dx. So I have two equation and two unknown values. So we can solve both equation and get the values of v1 dash and v2 dash. The two equations I am getting is, just a minute, there is one mistake I think. Yes, uh, this ax multiplied by this is equal to dx. So I will have ax here, or you can say divide this by ax, then you will have these two equations. You can directly solve this, or you can convert into matrix form and then solve it. Say, let me write it in matrix form. Equation will be y1, sorry, matrix form, if I want to write it, it will be y1, y1 dash, y2, y2 dash, v1 dash, v2 dash equal to 0 fx. You can just multiply the matrix and see yourself. This is the matrix form for this. I'm writing this in matrix form so that uh, uh, it becomes easier for me if I want to solve third order equation or fourth order equation and all. Now, this is converted into equation of the form, you can say ax equal to c, okay, where a is any matrix, x is column vector, variable vector, and c is also column vector. And we say that we will have solution of this equation, unique solution, only if a is invertible, or you can say non-singular. Now, since y1 and y2 are independent, that means these two columns, y1 by y1 dash and y2 by y2 dash, these two column vectors are linearly independent. Because of that, the determinant of this one, that is determinant of y1, y2, y1 dash, y2 dash, is non-zero. We call this to be Wronskian, W equal to this one. So determinant is non-zero. We can use Cramer's rule to find the solution of this matrix, or you can say we can use Cramer's rules to get the values of v1 dash and v2 dash. Cramer's rule says that if ax equal to c is any equation, or you can say system of equations, then xi will have solution equal to determinant of a, and this is possible only if a is non-singular. The numerator is determinant of ai, where ai means matrix formed by replacing the ith column by c. So here I am having y1, y1 dash, y2, y2 dash, v1 dash, v2 dash, 0 fx. From here, so from this I find that v1 dash, that is x1, v1 dash will be equal to determinant of a, means determinant of y1, y1 dash, y2, y2 dash, which is equal to, you can say, y1 into y2 dash minus y2 into y1 dash, and numerator will be determinant of, that is replace the first column by 0 fx, second column as it is. Then when you find the determinant, you will get fx y2 dash minus fx y2, sorry, not y2 dash, y2. So v1 dash is this value. Similarly, v2 dash is fx into y1 divided by this value, which we call it as w. So once you have v1 dash and v2 dash, you can get the values of v1 and v2 by integrating it with respect to x. to V1 dash, V2 dash, or directly simplifying also you can get the value. No need to go for the determinant form. Once you have this, you integrate the whole equation with respect to x. You will get the value of V1 and V2. Once you have the value of V1 and V2, you can substitute that value in your original equation. Since V1 is this value and V2 is this value, our original equation was y equal to V1x, y1x plus V2x, y2x. So this will be equal to, you can say, this V1 value into y1x and this V2 value into y2x. This is the general solution which includes yc plus yp. For example, if you have y double dash plus y equal to sec x, and if you are asked to solve this one, then first thing is you need y1 and y2. Y1 and y2 for this one will be, let us see, m square auxiliary equation. That is, I'm converting this equation first to homogeneous form and then getting the value solution for this one, this homogeneous equation, m square equal to 1, which implies m equal to plus minus I, or you can say y is equal to cos x, c1 cos x plus c2 sin x. For using if I'm using variation of parameter, I will assume that y is equal to v1 cos x, y1 plus v2 sin x. Then I will find y dash. Next, we will consider this part. First derivative of v is to be 0. So then y double dash will be minus v1 cos x plus minus v2 sin x, and then minus v1 dash cos x plus v2 dash, v1 dash sin x plus v2 dash cos x. Substituting these equation in this equation, you will get a second condition, and both the condition combining and simplifying, you will get the general solution of the equation. I think you have understood this one, but let me go for third order case. I'm talking about, say, suppose this equation. You can just see RHS value is sec 2x. In the earlier case also, RHS value was sec. So we are not much concerned with dx value. It can be any values, and very easily we can find the solution. This one method, since I'm already given y1, y2, y3, we could have obtained it also using auxiliary equation n cube plus 1, n cube plus 4m equal to 0, getting the value of m to be 0, then plus minus 4i, plus minus 2i. Or if I'm already given, then as we had done earlier, we will assume let y is equal to v1 plus v2 cos 2x plus v3 sin 2x. Then differentiate y, find y dash, y double dash. In this first case, the v1 dash, v2 dash part we will consider to be 0. Similarly, in the second case also, we will consider v1 dash, v2 dash part to be 0. Then we will find triple derivative, substitute in this equation. We will have 3 equation, 3 unknown. We can get the values of all the 3. But in place of this method, if I am using this Cramer's rule method, or you can say I am directly converted into matrix form, it becomes very easy. It is v1 dash is equal to Wronskian, which is y1, y2, y3, y1 dash, y2 dash, y3 dash, then y1 double dash, y2 double dash, y3 double dash, and numerator, first column RHS, that is 0, 0, sec 2x, second column as it is y2, y2 dash, y2 double dash, and y3, y3 dash, y3 double dash, and then we will simplify this. Substitute the values of y1, y2, y3 as cos sine, 1 cos 2x sine 2x, and then simplify. It will be 1 cos 2x sine 2x, then 0 minus 2 sine 2x, 2 cos 2x, this is 0 minus 4 cos 2x minus 4 sine 2x, and numerator will be sec 2x, then for second column cos 2x minus 2 sine 2x minus 4 cos 2x sine 2x, 2 cos 2x minus 4 sine 2x. When we will simplify, denominator is how much? Can anyone tell me what will be the denominator value? Yes, hello?
Is it 8, ma'am?
Yes, correct. And numerator will be? Denominator is correct, Tulsi? Numerator will be again cos square x. Yes.
2 sec 2x. 2 sec 2x.
Sec 2 sec 2x.
Yes.
2 sec 2x. Is she correct?
Yes, sir.
Okay. So 2 sec 2x you are getting in the numerator. Let me check it. Sin square x. Yes. Similarly, v2, or you can say, you can write it as sec 2x divided by 4. v1 dash. Sorry, this is my v1 dash. So what will be v1? Can anyone tell me? v1 will be equal to integral of 1 by 4 sec 2x dx plus c1. Okay. Similarly, v2 will be denominator will be the same, so it will be 8, and numerator will be we will write first term as 1 0 0, second term will be 0 0 sec 2x, third term is sine 2x 2 cos 2x minus 4 sine 2x. When you will simplify, you will get, how much you will get? -2, I think. No?
Yes, ma'am. -2.
Yes.
And
So I will
V1
be
is,
having -1/4.
and V1
So,
is 1 by 8 log sec 2x plus tan 2x.
yes, 1/8 ln
Log madam. Mod sec 2x plus tan 2x.
Yes, sec 2x cos 2x.
Sec 2x plus tan 2x.
Yes, this is normal integration of sec x, you can say, plus c1.
Yes.
Similarly, v2 dash, so v2 will be equal to minus 1 by 4x plus c2. And again, v3 will be same process. You will get the value of v3, or let us write only. This is 1, 0, 0. Last one will be 0, 0 sec 2x. And this matrix will be cos 2x minus 2 sin 2x, then minus 4 cos 2x. So this value will be how much? Minus 2 tan 2x. Yes or no?
Minus 2x.
Minus 2
Minus
tan
2 tan
2x, no?
2x. Yes, ma'am.
Okay. So now this will give me v3 equal to my will be equal to how much now? Integrate this. This is minus 1 by 4 tan 2x. So I think it will be 1 by 8 log cos 2x.
Minus 1 by 8.
Okay.
Yes.
No?
Sec 2x. Yes. Yes, ma'am.
So it will be 1 by 8 log cos 2x plus c3. So my yx is equal to now v1. v1 as you is 1 by 8, or you can say v1, that is this value. You will write yx is equal to this value multiplied by y1, which is 1, plus this value v2 value multiplied by second y2 was cos 2 multiplied by cos 2x, and v3 multiplied by sin 3x. That will be your final answer. Okay, that is the reason that the variation of parameter is a quite powerful method. The only problem in this is that integration. We should be thorough in integration, then we don't have any problem in this. Now let us go for another method of finding this particular solution, that is method of undetermined coefficient. This method is actually special case. That is, we cannot use this method in all second order differential equation, second order linear differential equation. In this case, our coefficients of second derivative, first derivative, and y should be constant. First thing, it should not be function of x. Second, my dx, RHS value should be either polynomial or exponential or sine or cos, sine x, cos x, or its multiplication. That is, it's just a special case for this one. Say suppose I am having equation of this form. Then CF, very easily we can find out what will be CF for this. Say, let me write it here. My equation is y double dash plus 3 y dash plus 2y equal to 1 minus x square. First I will write this yc value, or anyway yc is nothing but auxiliary equation is how much? M square plus 3m plus 2. So m plus 1 into m plus 2 is equal to 0. M is equal to minus 1 minus 2. So I know yc is equal to c1 e to the power minus x plus c2 to the power minus 2x. Fine. Which I can write it here. Now for finding yp, we will have a trial function. We will assume a trial function. Since my RHS, and it depends on my RHS dx value, you can just see it is a polynomial of second degree. So I will assume that my yp is polynomial of second degree, which is ax square plus bx plus c. Then, since we are assuming that this satisfies this equation, let us differentiate yp and substitute in this equation. Equation 1, derivative will be yp dash equal to 2ax plus b, yp double dash is equal to 2a. Substitute these values in the original equation. You will get 2a plus 3, 2ax plus b plus 2 ax square plus bx plus c equal to 1. Just a minute, let me remove this part. Equal to 1 minus x square. Now comparing the coefficients of comparing the powers of x. Say if I'm comparing x square from both sides, I'm getting 2a equal to minus 1. This one and this, which gives me a equal to minus 1 by 2. Then comparing x to the power 1, I am getting 6a plus 2b equal to 0. And a we are already having minus 1 by 2. So it will be minus, that is 2b equal to a is this one, so 3. Or you can say b is equal to 3 by 2. Is this correct? Next, comparing the x to the power 0, I am getting 2a plus 3b plus 2c equal to 1. Substitute the values of a and b in this. You will get 2 into minus 1 by 2 plus 3 into 3 by 2 plus 2c equal to 1. Simplify this. What will be c equal to? How much? It is minus 9 by 4, I think. Is this correct? This gets cancelled with this one. So this goes right side. So minus 9 by 4. And I assumed yp to be ax square bx plus c. Therefore, my yp is now equal to minus 1 by 2 x square plus 3 by 2x minus 9 by 4, or you can say y is equal to yc, which is c1 e to the power minus x plus c2 e to the power minus 2x minus 1 by 2x square plus 3 by 2x minus 9 by 4. And this is my final answer, general solution. Is this clear? This is the case when my dx was 1 minus x square. So I assumed my trial solution, or you can say that my trial function, to be ax square plus bx plus c. But suppose my dx is cos 3x. In this case, what should be the trial solution? Can I consider a cos 3x to be trial solution or not? Let us see what will happen if I am considering only a cos 3x as trial solution. So my equation y is given to me is y double dash minus 3y dash plus equal to cos 3x. Okay, let me check it again. Yes. And we are assuming yp equal to a cos 3x. Then y dash p equal to minus 3a cos 3x. Y double dash p equal to, this is minus 3a sine 3x, and it will be minus 9a cos 3x. Substituting this in this equation, what you are getting? Minus 9a cos 3x, then plus 9a sine 3x equal to cos 3x. Now if you compare this value is equal to this plus 0 into sine 3x, you can say you are getting your value of a to be 0 from these two, whereas from the other two you are getting the value of a to be minus 1 by 9. It's not possible. That is, a will be only one value. So that means we cannot take a cos 3x to be the trial solution of the equation. In this case, when sin x or cos x are in dx, or you can say are in RHS, then we consider trial solution yp to be a cos 3x plus b sin 3x. That is, we will take sine and cos both. Now let us substitute this in our equation. Differentiate and substitute. 3a sine 3x plus 3b cos 3x. Substituting these values in the original equation, we will get minus 9a cos 3x minus 9b sin 3x, then minus 9a sin 3x, sorry, minus plus, and then minus 9b cos 3x equal to a cos 3x plus b sin 3x. Comparing cos and sine, coefficients of cos and sines, we are getting minus 18a equal to, sorry, right side I am only having dx is this cos 3x. So substituting in this equation, I am getting this. So minus 18a is equal to cos 3x, comparing the coefficient of cos 3x, or you can say a is equal to minus 1 by 18. Again, comparing the coefficient of sin 3x, you have minus, how much we are having? Minus 9b plus 9a equal to 0. Or you can say a equal to b. So b is also, that means 1 by 18. So my yp is equal to minus 1 by 18 cos 3x minus 1 by 18 sin 3x. Find the value of yc also. Your final answer will be y equal to yc plus yp. I am considering different case, or what should be my assumption of yp. Now, if I am having equation in which my dx is e to the power 5x, let us take this one. But there is one, we could have directly taken, in this case, a e to the power 5x as the solution, but y double dash minus 10y first, but for this one, first let me find yc. Yc finding means I need auxiliary equation, which is m square minus 10m plus 25 equal to 0, which gives me m minus 5 square equal to 0, or you can say m is how many roots? two roots I am getting. I am equal to 5 comma 5. No? Is
Yes,
this
ma'am.
correct?
Yes, ma'am.
So my solution or yc is equal to c1 e to the power 5x plus c2x e to the power 5x according to the real and equal method we have seen in the starting. If I consider my yp equal to e to the power 5x, what will happen once we have the value of a? It will be because c1 e to the power 5x is there in my solution in my yc. It will get connected and c1 is any arbitrary constant. Say suppose a is 5. Then my final answer will be c1 e to the power 5x plus c2 e to the power x 5x plus 5 e to the power 5x. Now since 5 is a constant and c1 is arbitrary constant, I can combine both and write it as c3 e to the power 5x plus c2x to the power 5x. So now you just see I don't have particular solution in this case. So that means our assumption is wrong. That we have to take care for our assumption. We should check it that our solution yp is not same as yc given to us. So in place of this, I will assume yp equal to a x square e to the power 5x, because I'm not taking we say that for finding the solution we multiply it by simple polynomial, say x squared, x cube. Since x e to the power 5x is already the solution, second solution, so I will consider yp to be x squared e to the power 5x. Now we will differentiate this. Again differentiate it. Substitute these yp, y double dash, y dash p and y double dash p in the original equation, this one, and then simplify. You will get this again. Further I can write 2a to the power 5x plus 20 ax e to the power 5x plus 25 ax square e to the power 5x. So y double dash means 2a e to the power 5x plus 20 ax e to the power 5x plus 25 ax square e to the power 5x minus 10 2ax e to the power 5x plus 5ax square e to the power 5x plus 25 ax square e to the power 5x equal to e to the power 5x. Now compare the coefficient of e to the power 5x, x e to the power 5x and x square e to the 5x. You will get, or you can directly, if we can just compare coefficient of e to the power 5x, let us see what we are getting. 2a equal to 1. So a is equal to 1 by 2, and since I have only one arbitrary or only one constant to be replaced, so this is fine to me. So a I am getting to be half. So my yp is now half x square e to the power 5x. So y is, I can write it as equal to yc plus yp equal to c1 e to the power 5x plus c2 e to the power 5x plus 1 by 2 x square e to the power 5x. Now you can just see in the solution, or we have three different forms. Now let me talk about this example. Say if I'm having combination of these terms, that is e to the power ax 7x, and then the trial function you can consider is, you can just first just cross check it that your coefficients, or you can say yc, uh, what are the values of yc. Then after that, we can assume e to the power minus x for the first one. Then for the sine x part, you can say b sine x plus c cos x, because if sine and cos are there, we should have sine and cos both in our solution. And for x, I can say dx plus e. So this will be my yp. I will differentiate it two times, substitute in the equation, compare the coefficient of e to the power minus x, sin x, cos x, x to the power 0, and I will get the values of a, b, c, d, e, all the three. So, based on this, there are certain trial functions I've written this table. Say, suppose my dx value is e to the power mx, and one root of the auxiliary equation, or you can say all the roots of auxiliary equation are different. In that case, you can take a to the power mx, whereas one root is m. So naturally, as I said earlier, there will be c1 e to the power mx part in your yc. So to avoid that, we will consider trial function to be ax e to the power mx. If we are having two roots or two values of m, then in that case, our trial solution is ax square e to the power mx. For sine and cos case, you will consider b cos mx and c sine mx. For polynomial, if 0 is not root of the auxiliary equation, directly you can consider ax square plus bx plus c as trial function. If 0 is single root, in that case you take this as trial function. If 0 is double root, then again multiply by, what we are doing, we are just multiplying by x. So again multiply by x, and then you can just see this method of finding yp by undetermined coefficient is easier because there is no integration in our work. Okay, we were just differentiating, substituting, and getting the values of constants. So method is easier, but it is possible only for special case, not all case. Now, um, as I said in the starting only, that this second order differential equations, many applications are there in mechanical and electrical service circuits. So let us take a basic mechanical system, a spring which resist compression and extension, suspended vertically from the fixed support, and let us attach a ball with mass m, and the mass of the ball is such that it neglects the mass of the spring. Then in that case, what will happen, that by Newton's law, we have that there will be a force which is equal to mass into acceleration. And when the ball is attached, initially it is on a stretched position. When the ball is attached, it stretches down to a distance s naught, and the force, we will have a force, say F, upward. Let us take downward to be positive, upward to be negative. Then F will be equal to minus k s naught, where k is the spring constant. That is, to balance this stretch downward, we will have upward force F equal to minus k s naught. But this F naught doesn't have effect on motion of the body. The reason is this F balances with the weight of the ball. That is, you can say minus F is equal to W, or F plus W is equal to 0, where F is minus k s naught as we have seen, and W is mass into gravity, and this equal to 0. And we can call this to be equilibrium state. Now, from the position y equal to 0, let us stretch this ball downward to a distance say y. Then there will be a force applied which is equal to, let me call this as F1. Since ball is going downward, F1 will be minus k y, where k is staying constant, and going upward, that is why minus k. Actually, this F1 is trying to resist this ball, or you can say we call it as restoring force, pull the ball back or pull the body back. Then from the combining these two equations, as we have seen, my F1 is equal to minus ky. Combining these two, we will have force equal to, that is minus ky equal to, that force was force applied on the system or on the body, equal to m d2y by d square. This is for the case where damping is very small, or you can say we can neglect the damping. So the whole equation will be m d2y by dt square plus ky equal to 0. You can just see this is nothing but linear equation with constant coefficient, second order. And solution of this one is very easy. This is nothing but, let just d2y by dx square plus k by my equal to 0. Let me write this one. And then the auxiliary equation is r square plus k by m equal to 0. So r is equal to plus minus k by m I. Is this correct? Since r is equal to plus minus k by m I can write my solution to be cos k by m a plus b sin k by m. Y of t equal to this. K by m, if we are considering to be root k by m equal to omega naught, then in that case we have equation yt equal to a cos omega naught t plus b sin omega naught t. This is nothing but harmonic oscillation, which, and it has a period of 2 pi by omega naught. Therefore, the body executes cycle omega naught by 2 pi. Then in this case, if we apply or we add a damping force also, this is possible by adding a dash pot in the system. So if we add the damping force, and suppose, and we assume that damping force is proportional to the velocity of the motion, then in that case F2 or second force will be minus C dy by d2, where C is the damping constant, and this C is always greater than 0. The reason is, say suppose dy by dt is positive, that means it is going downwards, then F2 is negative, or you can say yc minus cy dash is greater than 0. This implies minus c is greater, sorry, F2 is less, since y dash going downward, it is positive, means F2 should be less than 0. This is less than 0. So this value will be less than 0, which implies that c is greater than 0. Now suppose y dash is negative, or you can say ball is going upwards. In that case, what will happen? F2 will be positive. F2 positive means minus c y dash is greater than 0. Now you know that y dash we have considered here negative. That means minus c should also be negative, which gives, then only it will be greater than 0, which gives me c greater than 0. So this damping constant c is always positive. And now my equation will be, in place of this equation we will add the second force also. So now my equation will be m d2y by dt square plus c dy by dt plus ky equal to 0, which in standard form we can write it in this way. Just a minute. This we can solve this equation because this is nothing but linear equation with constant coefficients and get the value of y. So auxiliary equation is r square plus c by m. I am writing r because m is already considered in this one. K by m equal to 0. So r is equal to or let us further simplify this one. It will give me minus c plus minus root c square minus 4k m divided by 2n. Now depending on the discriminant c square minus 4km, we will have three case, that is case in which c square is greater than 4km, case in which c square is equal to 4km, and c square is equal to 4km and c square is less than 4km. You will have three case and you will have three solution for this one depending on your y value. So till now, in our case, you can just see in our system there was only internal force due to inertia, damping, spring force. Now if we apply external force, say RT on the system, then our equation will be this one. And this external force we also called it as force motion. And since you, as you have seen that your solution was in the form of sine and case cos, let us assume that RT is in periodic form, that is f naught cos omega t. Then your equation will be m d2y by dt square plus m dy by dt plus ky equal to f naught cos omega t. This one now we can solve and get the value of y. For yc, directly we can write it or we can find it depending on the value of c. Yp, you can assume by undetermined coefficient method. Let us assume yp equal to a cos omega t plus b sin omega t. Substitute the values of yp, y dash p and y double dash p in this equation. Simplify and get the value of small a and capital A. Just substitute and see what you are getting. Are you following this? Can you find the values of yp? Okay, you find it afterwards. I have already solved it and written here. When you will substitute yp y dash p y double dash p in your equation, that is the equation of in this equation, you will get a equal to this value, b equal to this value. And then again, if you take uh, root k by m as omega naught, then in that case a equal to this value, a and b are these values, yc we know how to find it. So our general solution or our solution for this model will be yt equal to yct plus ypt. Now in this case, suppose c is equal to 0, that is undamped case if we are having, then as you can just see, b will be 0 and you will have this part also 0. So you will have a equal to f naught omega naught square minus omega square divided by m omega naught square minus omega square, the whole square. And yc, we had already calculated finding the yc value, y double dash plus k by m y equal to 0 part, which was this value we had already calculated. So our final solution will be yt equal to a cos omega naught t plus b sin omega naught t plus f naught by m omega naught square minus omega square cos omega t. If we consider in this case cos omega t with maximum amplitude, that is if we consider this to be 1, then in that case this value will be, you can just sorry, this value will be 1 and my a, that is a part, will be equal to f naught divided by m by omega naught square minus omega square, taking k by m, or they can say taking m constant, we can write a equal to this value. So you can just see as omega tends to omega naught, omega and omega naught are two different values that will not be equal because omega naught is the natural frequency we are getting, whereas this is the forced one. So it will not be equal. But as this tends to omega naught, our rho and a become infinite, or you can say our motion is infinite motion, or it is for the long term. Motion will be for long term. If we consider the case in which c is greater than 0, that is damped case, then uh, our equation was my double dash plus cy dash plus ky equal to 0, and we considered f naught cos omega t. We find that in this case, if we substitute c and simplify, we get as t tends to infinity, that is when t increases, as t increases, our free oscillation, that is c of part, becomes 0 and we have only forced oscillation part remaining. Let us have another, or you can say, suppose I am having this example, and can you write model for this one? Mathematical model for this problem. This is mass spring problem. I have taken it from book. See, in this case, weight of the ball is given to be 16 pound. So mass mg is equal to 16, or you can say m is equal to 16 by g, which let us take as 32. So 16 by 32 m. So now you are having m value, again spring constant, that is k, you are given as 1, Resistance in the spring system is numerically equal to the instantaneous velocity. That means C is equal to 1. Then initial, it is initial value problem. Initially it is given that at t equal to 0, weight is in motion from a position 2 feet. That is y0 is equal to 2 below its equilibrium position by giving its downward velocity, initially giving its downward velocity 2 feet per second. That means y dash 0 is equal to 2. So these things I know. Mg, that is m I'm having, k I'm having, c I'm having. I can substitute this. I don't have any outward force, so I can substitute in my equation. Equation is my double dash plus cy dash plus ky equal to 0. So substitute the values, you will have your answer and model. So you just see, this is the model for this problem. So similarly, you can write model for any other problems. Now, if I talk about oscillatory electric circuit, say suppose I'm having an electric circuit which containing inductance, capacitance, resistance, and voltage drop at inductance at L or inductance B, L dq by dt. Similarly, at capacitance B, say Q by C, and resistance B, R dq by dc. Then you know by Kirchhoff's law that voltage applied will be equal to 0 because there is no outside voltage. So this will be equal to 0. This can be further simplified by taking or dividing the whole equation by L. You will be having standard form d2q by dt square plus r by L dq by dt plus q by lc equal to 0. Considering r by L as say value 2 lambda, then 1 by lc as mu square, you have standard equation of this form. Now you can see that this is nothing but homogeneous equation with constant coefficient. You can solve it very easily. You will get the value of q, that is charge at time t. If in this system we add voltage or EMF P cos nt, then my equation now RHS will, or you can say dt part will be this, and I will have this equation. This equation you can solve it very easily using undetermined coefficient method. Can you solve and tell me the value of Q? Yes. What will be our Q value in this case? Let us see. Hello?
Yes, ma'am.
Can you solve it?
Yeah, this is a constant coefficient differential equation which is a non-homogeneous. So first we will solve the homogeneous problem.
Yes, first
Um,
CF part, YC part you will find out.
yeah,
Then PI part you can find out. There are many, we all know there are many other methods of finding PI, particular integral
yeah,
part. Okay, so any method we can use, but since today we are talking about variation of parameter and undetermined coefficient, you can use any one of them to
yes,
solve this and you will get the answer. But okay, uh, can you write the model for this one? Say suppose I am having this problem, read the problem and write the model for this initial value problem.
and this is LCR circuit problem.
Yes, LCR circuit problem.
Yeah,
And
external force is also
LCR circuit problem, when we are having, what is the equation of LCR circuit? We have just now written L
yes, yes,
d2q by dt square. So L d2q by dt square plus this is q by c r dq by dt and q by c. So r dq by dt plus q by c equal to whatever RHS value is.
ET, external
dt,
voltage.
okay, dt, fine. So what is
ET.
L, what is R, what is capital C, and what is dt?
R is the resistance, Q is the, I think,
So here initial charge,
yeah,
we
charge.
initial charge of 2 coulombs on the capacitor. Okay, that means Q0. Initial charge means Q0 equal to 2. This much first line tells me this. At the instant the circuit is closed, the current 3 ampere is present. That means I initially I0 equal to 3, or you can say I means dq by dt. So q
Yeah.
dash 0 equal to 3 we can say. Then in this circuit the okay, external voltage is also there, means dt
Right hand side,
equal to 20 cos
cos T.
t. In this circuit the voltage drop across the resistor is 4. So R is 4.
4 times of instantaneous
Sorry,
charge.
4 times the instantaneous charge. So I should have written equation 4 dq by dt. Voltage drop across R. Voltage drop across capacitor is 10 times the charge, means 10 cube. And across the inductor is 2 times the instantaneous change in current, means 2 di by dt
Which is dq,
equal
d2
to
cube upon dt2.
2 cos t, and since di by dt, since I is dq by dt, I can write 2
d2
d2i
cube
by
upon
dt square plus 4, sorry, d2 q by dt square dq by dt plus 10q equal to 20 cos t, with q of 0 equal to 2 and q dash 0 equal to 3. This is the model of initial value problem. We can solve it, get
Yeah,
the
we can
value of
use any
q
method.
in terms of t. Till here is fine. Now see, whatever I explained today, it was method of solving second order equation, and we can very easily the same process we can apply and find solution for more than second order equation also, as you have seen in the variation of parameter. Similarly for undetermined coefficient also, depending on your dx value, you can take the trial function and then solve it for higher orders also. Even we can use this second order method for solving partial differential equation also. Okay, this was this I have taken it from one of the faculty who is working in this differential equation, partial differential equation only, Dr. Lakveer Kaur. Okay, so in this case, let us see how we are applying or how we are using second order method in this one. Say suppose we describe G dash by this expansion method for traveling wave solution of non-linear partial differential equation. This is just for your knowledge. If you all are interested, you can go further, you can study further. Okay, so suppose we have a non-linear equation with two independent, because it is non partial differential equation, that naturally you will have more than one independent variable. So I am having two independent variable x and t, and my equation, or you can say p, is the polynomial in uxt. So equation is in polynomial form with independent variable x and t. This equation will be partial derivative and non-linear terms are also there. Suppose non-linear terms are also there in this equation, then there are steps for solving these types of equation. That is what we will do is, since we are having uxt, that is more than one variable, one independent variable, we will convert into single independent variable by assuming independent variable xi equal to x minus vt, where v is any constant. then naturally uxt will be equal to u xi, and xi will be equal to x minus vt. So now my this equation for the polynomial, u will be as it is u, fine. Sorry. Then ux will be, you can just see, ux means partial derivative with respect to x. So this I can write it as, because xi is equal to xbt, I can write it in terms of derivative of xi as du by d xi and del xi by del x, which is 1. So this will become du by dz, dz, which we can call it as u dash. Similarly, next term is ut. That means du by dz, dz by dt. Dz by dt is minus v. So you will have next term to be minus v u dash. Similarly, double derivative, if you are doing it, differentiated 2 times, and we will have polynomial of this form by just substituting xi equal to x minus vt. Now my equation is, or you can just see, ordinary differential equation in place of partial differential equation. Next, we will assume that the solution of this equation is of the form alpha m g dash by g to the power m g dash by g to the power m minus 1 and all. That is, we are writing the solution of this equation to be polynomial of the form g dash by g, where g is solution of the second order equation, g, where lambda, mu, naturally initially we don't know the values of lambda, mu, alpha m and alpha m minus 1 and all values, that we will find out by solving it. Next, this m value, the first thing is that what should be our m assumption. It depends on our derivative, that is highest order derivative, and the non-homogeneous non-linear term appearing in, that is, by creating a homogeneous balance we will assume our m value, and then find the usi, we will write it, substitute in our original equation, that is equation 3, or solved equation 3, simplify, we will have algebraic equations, and that algebraic equation, when we will simply solve it, we will get the values of that lambda, mu, v, alpha m. Once we have these values, we have our value of u. For example, there is one kdv and mkdv equation, which is, this is traveling wave equation only, wave propagation of bounded particle, sound wave and thermal pulse equation. I have this. In this case, we assume that let xi is equal to x minus vt. Then if you substitute this, then this equation becomes minus v plus alpha u, sorry, minus v u dash plus alpha u, ux will be u dash plus beta u square ux, that is differentiating u, ux when we are talking about means del u by del x. Now when you are converting into xi form, it will be del u by del xi by del x. Del xi by del x is 1. So you will have uxx equal to 0. Integrate the whole, sorry, not, let me write it again, minus v u dash plus alpha u dash plus beta u square u dash plus u triple dash equal to 0. Integrate the whole equation with respect to xi. So you will get constant minus v. What will be the integral value? Can you tell? Can anyone tell me? Integral of u dash with respect to xi, du by dxi with respect to xi integral. When you will do it, you will get the value u. So this will be u plus integral of u dash, u into du by d xi d xi. So that means u du we are talking about, which gives me 1 by 2 u square, or you can say alpha by 2 u square, plus integral of the third term will be how much?
It will be beta u cube by 3. Yeah, because, yeah, yes, ma'am.
Okay, and the fourth term will be,
This is u triple prime.
yes, u triple dash, then it will be u double double dash, no, equal to
Yes,
0. So in
yes.
this case, we will assume our solution u xi, or we will assume that we are saying that our solution is alpha m g dash by g to the power m, where it is in the step 2, we are assuming in this form. So we will assume our solution to be alpha 1 g dash by g, that is m I am considering as 1. The reason is, you can just see u cube and u, the highest derivative is 2 and non-homogeneous part is 3. So the balance will be 1, m equal to 1. So we will consider u xi equal to this value. Find u double dash, u triple dash, u cube, u square, substitute in this equation, and then get the values of this v, alpha, beta, and all. You can solve it very easily. But if your equation, in this equation, you are having only uxx, that is partial derivative, third order partial derivative we are having. But if it is more than that, that is naturally manually becomes a bit difficult. Then you can use the software Maple or other software and get the values. So this is all for today's talk. Any question, anyone? Yeah. So I think there is no question,
So, any queries from the participant side?
no queries.
Yes, ma'am. So, thank you very much, ma'am, for sharing your profound knowledge and expertise about differential equations with all the participants. Most importantly, that in this lecture, we just start with the basic method to solve the partial differential equation or the ordinary differential equation. And then after we switch to the application of linear ordinary differential equation, which can be utilized in the research to solve the more complicated problems which usually arise in the mathematical modeling, and it comes under the category of partial differential equations. Ma'am, you really elaborate the concept of reducing partial differential equation to the ordinary differential equation very beautifully, and it can be used by any of us. And you explained each and every step in a very detailed manner. I hope all the participants have really explored this session content and conceived it in a very elaborate manner. So, thank you very much, ma'am. And we are thankful to all the participants also. Now, I would like to request to please switch on your camera so that we can have a group photograph.
Thank you, everyone, so for listening patiently.
So, thank you to all. Now, I extend my greatness to all the participants as well as all the faculty members of the mathematics department. Moreover, we are very much thankful to Professor Alka Tripathi ma'am, who is not working actually in the differential equation. Even then, ma'am explained each and every step related to this session content in a very uniform manner. So thank you, ma'am. Thanks to all the participants. So tomorrow again we will connect with the same link at 3 p.m. So thank to all of you.
Thank you.
Thank you.